Okay, so we are going to continue the same topic pure bending today first, and then I will start the new topic. Okay, because last time we couldn't complete this section pure bending. Just to refresh your memories, what you have learned last time. We are learning about bending as a special way of another load type, right? Bending loads. Members subjected to bending loads, we call them beams, right? And under that, first we are learning pure bending. It's a special case of bending where the external loads are applied as bending couples, right? So we learned it last week like this. So in this kind of load application, if you cut the member at any point and see what is the internal forces, right? What are the internal forces? You find that there's only one internal load. That internal load is a moment. We call it a bending moment. And that bending moment, magnitude wise, equal to the externally applied bending moment, M. And it is constant along the beam, same bending moment along the beam. So therefore, it is a simple case of bending. And for this simple case, we are learning how to find out the stresses developed and also the deformation, how to quantify the deformation. Okay, so let me show you the outline. We started last time. So we talk about the strain, okay, and then using Hooke's law, we learn how to find out or calculate the stress using bending formula, okay, and then we learn how to quantify the degree of deformation using radius of curvature or uh, reciprocal of radius of curvature 1 over rho we call curvature. Okay, using those two quantities we can quantify and measure the degree of deformation. Okay, and then I have extended this theoretical concepts to analyze bending members which are made of several materials, two materials, because all the equations we have derived are relevant only for beams made of same material, single material. So then if the beam is made of different materials, how to solve that problem we discussed last time. So today, what I'm going to introduce to you is a special load application case we call eccentric axial loading, where internally the member going to subject it to there are two internal resistive loads. One is axial load and the second one is the bending moment. So now we know how to find out the stresses when there are axial loads or normal loads, and also now we know how to find out the stresses due to bending moment. So by combining them together, we should be able to tackle problems of that with the eccentric axial loading. So that's what I'm going to teach today. Just to recap what we have done now, you might not have this slide in front of you now in your lecture note, because this slide you can find it at the end of the lecture note, right? So I have just put in here just to show you that these are the things that we have learned last week. So what we did last week, we learned how to quantify or how to analytically find out the strain of, let's say, different layers of fibers. Okay, so those questions now we are asking about the final year project, I will answer in the during the break. Okay, and then we learn about the strain epsilon x, right? And there we learned that epsilon x is equal to negative y over rho, right? And then using Hooke's law we found out the equation for stress, at any point on the cross section, sigma x, and it is negative mi over I. Here I is the moment of inertia about the neutral axis. And every beam has a neutral axis. We learned that one, right? On the neutral axis, there's no force. Therefore, stress is zero. So here in this diagram, this is the neutral position of the neutral axis. And normally for single material members, this neutral axis going to pass through the centroid of the geometry. Centroid is the geometric center of the geometry. Okay. So last week we learned how to find out the centroid of a geometry. And then we learned that the stress vary linearly within the cross section. Maximum stress happens at the outer surface, depending on the way the load is applied. Top surface above the neutral axis can be compressive or tensile. Okay. Now, when the moment is applied in this manner, like this, we call it a positive bending moment. Right? Positive bending moments create a negative stress on the top surface. That is a compressive stress. So here, the maximum compressive stress going to be at the top surface. And at the bottom, all the layers of material going to stretch. So they are under tension, therefore tensile stress. So maximum tensile stress is at the bottom layer. Okay, so that is what we have learned last week. And also we learned how to find out the radius of curvature using known information like the bending moment, material property, E, right? And also the geometric details of this member, I, using this equation. Okay, and after learning these two equations, then we have extended our understanding to analyze members made of several materials. There, I taught you a method called transformed section method, right? In the transform section methods, we transform the two material member into a, or cross section of that member into an imaginary cross section made of single material. So once you do that, we can apply our bending formula, right? In that transformation, one member or one material going to be converted into an imaginary material, right? So that uh, we do that one without changing the height of the member. We maintain the height, but we increase the width. So how much we increase the width? By a factor of n, and the factor of n depends on the Young's modulus of the two materials. So n is given as a ratio of the two Young's modulus of two material. Okay, right. So once the calculation is done, we get the stresses for the imaginary section. Then to find out the stresses on the original or real section, we need to transform the stress values in the imaginary section into original section, right? Again, it is done by multiplying the imaginary section stresses by the factor n. So once you multiply by factor n, then you get the stresses on the original section. Okay, so that's what we have done last time. For today, we are going to learn about eccentric load, or members subjected to eccentric load. First, understand what the eccentric load means. Eccentric load means loads applied away from the major axis or the centroid of the member which is subjected to bending. Now here one example, lamp post. On this lamp post, you can see that there's a lamp on the top here. It has a mass. So if I consider the mass in here, so because of this mass of the lamp, the member or vertical member or the lamp post going to bend like this. So lamp post is under bending, or it's a beam, like a beam, right? Vertical beam. So, but if you cut this member at any location and see what is the internally generated resistive loads, you find two loads. That is, one is the axial load, which going to go through the centroid of the cross section. The other one is a pure bending moment. So it's a combination of two loads. So up to now, we didn't learn how to find out the stress when there are two loads applied on the same cross section, right? So now I'm going to teach you that. So we'll take another example similar to the lamp post, that is this clamp we normally use for woodworking, to clamp two pieces of wood together. Once we clamp the wood, then we can see that because of the loads applied on the jaw, the vertical member here, it is going to subjected to bending, and also there are going to be axial loads. So to find out that, what we can do, we have to cut this vertical member in the section CC prime. It can be any point along this vertical member, and see what are the forces applied. Right. So first we see our externally applied force 600 Newton, and then on the cross section there should be internal resistive forces. The first internal resistive force is to counter this axial force. So there should be opposite direction force P, and it should be equal to the externally applied load. But once we apply that one, we can see that this FBD is not still complete, because there's a unbalanced moment. P together create a couple, right? So to counter that, we need to introduce another, or the system, the vertical bar need to create a resistive moment. That resistive moment is M. If you want to find out the size of this resistive moment, it is equal to the externally applied moment, that is P, into the distance between the line of action of these two. So if you want to find out this M is equal to P times, if this distance is D, P into D. Okay, so internal moment is equal to P into D. So there are two loads now. So how to find out the stress at this section? So that is the question. Okay, so let me show you how to do that. Again with another example. So here in the first diagram on the top here, you find a, again, eccentric load applied member. So why it is eccentric? If you look at the section DE of the member, the DE going to subject to some resistive load. I mean, internally there are going to be some resistive loads, but there's no directly applied load along the major axis of DE. The loads are applied eccentrically, right? So if you want to find out the internal forces, again, you need to cut it between D and E and draw a free body diagram. So this is that free body diagram drawn. Okay, and like before, the first thing that we marked is the externally applied force P. Here it is marked as P prime. It's okay. P and P prime are the same. And then internally, there should be a resistive normal force F, and this F should be equal to P. Okay, and then we need to apply a resistive torque M here, that is to counter the moment or couple created by internal force P and external force P. Together create this couple, right? Right. So yeah, somebody, can you switch off your microphone? Thank you. Okay, keep your microphone switch off. All right. So now, if you want to find out the stress at the cross section, we need to first find out the size of these internal forces. First one, we know that, right? The internal force F, that is the normal force, should be equal to P. And the moment now we know how to find out, it should be equal to P times D. So once you know those two, then we can see the stresses caused by these two forces separately. So I'm trying to help you to visualize that information. Okay, now this Wang Pang Ching, you are not keeping your microphone switch off. Could you switch it off, please? Okay, right. Now, once we apply the normal force P, we know that they are going to be uniformly distributed stress, right? So that is what I have marked here in, let's say, I mark it as 1, 1. So this stress here, P, should be, sorry, stress sigma 1 should be equal to P over A, right? Is uniformly distributed. And then there's a internal bending moment M. Internal bending moment M going to create again axial stress. That axial stress we know how to find out using this equation, bending formula. And this bending formula tells me that it is not a uniformly distributed load, but it is a distribution linearly distributed. So that linear distribution, depending on the way the force is applied. Now here you can see that from the way the force is applied, the moment is applied or the force is applied, this member on the top DE going to bend like this, right? Can you visualize that one? So that means the top portion here going to be under compression, and the bottom side is under tension. You can see that, right? So therefore, the distribution of stress on the cross section due to applied bending moment going to be on the top compression, at the bottom tension, and the distribution is like this. Okay, so now this is the second load case, bending moment due to M, and this is due to F, which is equal to P, and this M is equal to P times D. And you know how to find out this stress. It is given by sigma x at any point along the cross section equal to negative my I. Okay, so now the stress state of the whole section is the addition of these two. We call it is by superposing the two stress states for individual loads, we can find out the total effect. So once you add tensile stress caused by force F with the compressive force applied in the top here, then you get a stress which is less than the tensile stress in the first case, right? So that is why here smaller stress on the top. And the bottom, you can see in the first case is tensile, and the second case also tensile. So once you add them together, more tensile force, then a longer or size of the stress is higher. So finally, we get this kind of resultant distribution. Okay, so analytically, as with equations also, we can write the same thing this way. Sigma x, that is the stress at any point on this section now, is a result of stress from the normal force and the stress resulting from bending moment. So sigma x plus sigma x bending. So I meant to differentiate. I mentioned it as sigma x centric. That means it is the stress applied at the centroid or the center of geometric center of the section. Right, so sigma eccentric is written as P over A, normal stress, and this is the bending stress. Okay, so once you add them together, we can get the equation of the stress distribution of the resultant stress distribution. So this is the equation of this line. Okay, so with that equation, we can find out the stress at any point on the cross section. Hope you understood that. Okay, so now let's apply this one for a simple problem. It's not a simple problem, but eccentric load case. Okay, let's read this one together with me. What it says, an open link chain is obtained by bending low carbon steel rods into the shape shown. So this is a chain, one link of the chain for 700 Newton load. So the load here applied is 700. Determine the maximum tensile and compressive stresses. Maximum tensile and compressive stresses. We know that maximum stress is going to happen on the outer surfaces. So which side is tensile, which side is compression in this member? So from the way the loads are applied, you can see that this one going to open up like this, right? So there won't be any stresses generated in those open areas. So stress is going to generate in the opposite side. So from the way the load is applied, the vertical part of the opposite side, which is a circular cross section, which side is tension and which side is compression. So let me mark this side. So can somebody tell me whether that side is under compression or tension? I want an answer from you to see whether you can visualize it and tell me, because later you need that kind of ability, right, to solve the problems. What is the stress? Is it tensile or compressive? You can see how the vertical part going to bend, right? From that, you can see how things going to, the whole vertical part going to bend, and which side is under compression, which side is under tension. So the outside, which I marked as with a red arrow, is it that side under compression or tension? That's my question. I need an answer. Are you listening, or are you sleeping? You're with me, right? Tension. Oh, that side is tension. Okay. Thank you for that answer. But think about how it is, yeah, going to bend. So if I just draw how it is going to bend, the middle line, if the middle line here is straight, after the load is applied, this middle line going to bend like this. Am I right? Right. Therefore, the outside is under compression. Okay. It's okay to make mistakes, then you learn it. Okay. So this side is now under tension. So we need to find out the maximum stresses in the outside and the inside. So that means those are the maximum tensile and compressive stresses. Okay. So part A. Part B, distance between section centroid and neutral axis. Okay, that part may be difficult to understand at this moment. So first I will complete part A, then you will see the way forward for the part B. Okay, so when we are solving this kind of problem, first we draw a free body diagram and open up our internal forces, then quantify the internal forces. Once you know the internal forces, then we can find out the stresses caused by each internal force and add them together. Then you get the resultant stress. Okay, so that is the approach. So first I cut the member at one location at point C, and then open up it, and I can see the internal forces. So first internal force is going to be the P, which is in opposite direction to the externally applied force, and that will create a couple. So therefore, I need to apply a resistive couple inside the member, that is M. Okay, now we know that this P, let's say this is F, should be equal to F. Okay, and this M should be equal to that F into the distance between the two line of actions of the two forces, D, F into D, right? So that is what I'm first finding out. So P is equal to 700 Newton, and M is the force into the distances between two line of action of the forces. Therefore, I calculated the internal moment. Okay, now once you know the two forces, it is easy to find out the stresses. So this P going to create a normal stress, right? We'll mark that normal stress as sigma. Okay, and that sigma should be equal to P over the area over which it is applied, because it's normal stress or normal force, right? Normal force create normal stress. So we know this one. Once we calculate A, we can find out that stress. So cross-sectional area here is circular. Okay, and the diameter given as 12 millimeters here. So this diameter here is D. I use capital D, is 12 millimeters. Okay, so that means 6 millimeters radius. So now I can find out the area by r squared, and by substituting r is equal 6 millimeters, I get this value. Okay, and then the stress, which is uniformly distributed, I calculated it as 6.2 megapascal. So that is what I have visual drawn here. Okay, so it's a uniform distribution, tensile. And then the second part is from the bending moment, right? M, internal bending moment M, and we know that it will create a bending moment, sorry, bending stress. It is also axial stress, normal stress. Sigma x is equal to negative my I at any point. So we are interested in the maximum stresses. Therefore, if I mark the sigma max is equal to mc over I, so I'm taking the magnitude only. So I omit the sign. Okay, so there I know m, I know c, and what is I? For circular cross section, I is given as pi by 4 if the radius here, this radius is r, it is r to the power 4. Okay, so with that information, I can find out this I. So that is what I did first. I found out the I for the circular cross section, and then substitute in the equation. So I got this value. Now this is the maximum stress. And previously we learned that inside it is tension, outside it is compression, right? So now I'm going to, the size of those compressive stresses and the tensile stresses are the same because it's circular cross section, right? So therefore, now outside they are going to be negative 66 megapascal stress, and inside they are going to be positive tensile 66 megapascal. Okay, so we have the diagrams, can visualize it. We did the calculation, we know the magnitude. Now add them together. Okay, so when you add in the inside part, so this is tensile, tensile, this is also tensile. So the total stress going to be higher tensile stress, and the other side, this is tensile and this is compression, negative, right? So once you add, that side going to be compressive but smaller compressive stress. So this is how you see it. Okay, so here 72 megapascal going to be equal to 66 plus 6.2 megapascal. Okay, here negative 59.8 is actually negative 66 plus positive 6.2. Okay, right? So we got the values of for the part A. This is part A. Okay. Now I'm going to read the part B with you. Okay. So part B says distance between the section centroid and the neutral axis. So here it is neutral axis. This is centroid. So why we need to find out this? Because when two loads are applied like this, our neutral axis will not going to pass through the centroid of the section. So you can see it, right? Once you construct your uh, final distribution of stress, you can see that it is a line like this, right? And the neutral axis is going to be where the stress sigma is equal to 0. Okay, but our centroid is the geometric center, right? It is still at the center of the circle. So now neutral axis is about YO away from the centroid. So we need to find out this distance. So we can do that if you take the equation of this line. Previously, can you remember the equation, how we wrote this equation? Sigma x is equal to the externally applied, not externally, the normal stress plus the stress due to bending moment. So it is a negative one, right? My over I. Right. So P over A is a constant all the time, uniformly distributed. Only variable in this equation is Y. So as the Y value vary from 0 to maximum value, sigma x vary. Okay. So now what we need to find out, what is the stress when Y is equal to YO? So when Y is equal to YO, sigma x going to be equal to 0, because at that point the stress is, you can see, 0. That is where the neutral axis is. So now in the equation, I'm going to substitute YO instead of Y. Okay, and this value should be equal to 0. Okay, so now here we know the P, we know the A, right? And we know M, we know I. So only unknown is YO. So you can find out the YO. So this is the answer. Okay, right. So now what we did, actually, we learned two load cases first, that is axial loading and next pure bending. We learned how to estimate stresses individually for each load. Now here in the eccentric load cases, we try to put them together and try to find out the combined effect. Right. So that is, again, we are now integrating the knowledge, right, and trying to solve complicated problems. Right, let's try another question, a similar one. Okay, first we need to understand the question, visualize it, and then you can see the way forward. So read the question. The largest allowable stresses for the cast iron link. So what is given is a link, cast iron link, are 30 megapascal in tension and 120 megapascal in compression. So you can see that it can withstand low tensile stress but high compressive stress. Those are the maximum values given. Determine the largest force P which can be applied to the link. Okay, so the load P is a compressive force, right? It's not pulling, it is pushing force. So once you apply the compressive force P there, internally they are going to be stress, but that stress is not uniform in the cross section. Why it is so? Because load P is not applied through the geometric center. If the load is applied to the geometric center, then there won't be any bending. is right. So to visualize that one, you have to take the cross section at AA. So this cross section here, and it is drawn at the bottom. So section AA is a T-shaped section. In the T section, if you mark the centroid, maybe somewhere here, and the distance to the centroid from the bottom surface is given as y bar here, right? The force is applied or go through the line of action of the force going to go through this point D here. So it is eccentric load, right? It is off-centered by a certain distance. Okay, right. So now, because of that, what is going to happen? This link going to bend. So can you visualize how it is going to bend? So if the middle portion going to bend, and then on the top, what kind of stress going to generate? Is it a tension or compression? Now, again, I'm expecting an answer from you. See whether you can answer that one. So on the top, it is going to be tension or compression now. Okay. Aha. On the top, it is compression. So visualize how it is going to, bend. Then you can tell how, whether it is a tensile or compression. So I'm going to take the line of action of the force P as a straight line, and after applying this load, that straight line, what is going to happen to that one? It is going to bend like this. Am I right? So if you bend it like that, the top surface is going to stretch, bottom surface is going to compress, right? So therefore the top layer is under tension, bottom part going to be under compression. Okay, right. So if you miss that part, you won't get the right answer here. So you need to know exactly, because here tension maximum is 30 megapascal, compression is 120. Now we know that point A here is under tension, and its maximum tensile stress there should be less than 30 megapascal to avoid the failure. And the bottom point here, B, is under compression, and the maximum compressive stress should be less than 120 megapascal. So basically, once you calculate the force P by considering those two requirements, you will get two values for P in this question. So later, we have to make a decision which one is the right one. Okay. All right. So now, first thing that we need to do, we need to find out the internal forces. So you can cut this member at AA, and if I just draw a simple diagram here like this, maybe not like this. Okay, this is the member like this. Right. So once the load P is applied here, P, there are going to be a force P like this, right? Internal force, and then a bending moment. So we don't need to know the direction. We simply put like this. So we need to find out the values of those two. So that is what it says. Determine the equivalent centric load, that is P, and the bending moment, that is M. Okay. And here we are going to use for the bending moment our bending formula. Yeah, we need the value of I, and also I need the distance to the centroid, y bar. If you know that one, then we can find out I easily, right, of this cross section. So in a previous calculation, we used the same cross section. Therefore, I'm not going to do that calculation, okay, to save some time. So the cross sectional area A here is this much. You can refer to the previous calculation. There we did the calculation, okay. And Y bar, we calculated it as 38 millimeters, okay, and I is this much. So we can straight away use these values and then do this calculation. Okay, now we know the Y bar, I, and A. So what are the unknown things here? We need to find out the centric load P, right? This is what we need to find out. And the bending moment M is going to be P into D, and the D is I'm going to go back, the distance between the load applied, that is D, up to the centroid. So this is the distance of D, right? So then we need to find out, so maybe I will redraw the internal force because it is not in the middle, right? So it is somewhere here like this, P, and the centroid somewhere here. Right? So therefore there's a gap. So that gap is the D. So if you want to find out that that's D, this is equal to Y bar minus 10, right? 38 minus 10, that is 28. So that is what I find here. Okay, so now I got the bending moment, internal bending moment in terms of P. Okay, right. Now it is time for me to find out the stress due to axial force first. Okay, we'll take it as sigma A. Oh, sorry. I'm going to find out the stress at point A and B because A is under tension, right? We learned that it is under tension, and this is compression. So sigma A consists of two components. That is the stress due to the axial load and the stress due to the bending moment. So bending moment, the maximum bending moment on the top, we can find out from this equation. Sigma 1 is equal to mCA over I. Here CA is the distance to the outer fibers, outer surface from the centroid. So I already calculated that value CA here. It's 22 millimeters because total height is 60, right? 60 minus 38, 28. Sorry, 22. And the bottom surface for the centroid is 38 millimeters. Okay, so for the bottom surface, it is a compressive stress, right, given by mCB over I. So can you write the sigma A now? Stress at A has two components, that is P over A, and it is a positive or negative component, P over A. Is it compressive or tensile? It is compressive, right? So that is why I mark it as a here, compressive force. Therefore, it is negative. So you need to introduce a negative sign here. Okay, and then the bending moment creates a positive stress, right? Therefore, positive, and it is going to be mCA over I. So we know all the values now except for P, A, M, C, A, 9. So therefore, I can write the answer here, P over 3 into 10 to the power minus 3. This is the area, plus M is given in terms of P, 28P, into 0.022, that is the CA, divided by I. I already calculated 10 to the power minus 9. Okay, so you do the simplification, you get this answer. It is 377 times P, a positive value, that is a tensile stress. And the bottom surface, sigma B, and here you can see, but still negative stress at the bottom from the axial force. So it is P over A. And from the bending moment, there are going to be compressive stress there. Therefore, negative mCb over I. Okay. And again, we can, oh, here I missed this negative sign, right? So put the negative sign. Okay. So it is going to be negative P over A and negative M, again the same thing, 0 to 8 times P. CB we calculate as 0.038 and divide this one by same I, 10 to the power minus 9. Once you simplify, you get a negative answer. That is compressive stress. Now we can find out which one is the critical load in the using the given maximum stresses. We should be able to find out the maximum value for P. So we know that sigma A maximum here on the top should be less than 30 megapascal because it's tensile stress. Therefore, 377 P is the sigma A. It should be less than or equal to 30 megapascal. So I will use this equal sign to get the maximum value, 30 into 10 power 6. So you simplify this one, you can get the answer for P. This is the first one. And sigma B is negative 1559 P, and this should be less than or equal to 120 megapascal. Okay, but now this one simplify, you get 77 kilonewton. Right. And here I think one thing very important you might mix up, I also forgot to put that one, there should be a negative sign here, right? Because it's compressive stress negative, otherwise you will not get this force P as 77 kilonewton. Okay, now we get another value for P by considering compressive failure. So you can see that the lowest load that we can apply, or largest load that we can apply, is the lower force here, 77 kilonewton. Okay, so once we apply 77 kilonewton, this member going to start fail by compression, not by tension. Right? Okay, I hope that it is clear. We did 2 questions on eccentric loading. Right. So the next slide is to extend this understanding about eccentric loading into 3-dimensional load case. Okay, so I'll leave this one for the advanced learners in this class to read and understand. It's very simple. It's like extending our understanding into 3 dimensions. So I'm not going to go into details here. Let me wrap up by showing you the summary of things that we have done so far under this topic. We learned about pure bending, and then we learned 2 very important equations. The first equation is the bending formula, sigma equals negative mi I, and then how to quantify the degree of deformation using radius of curvature. And next, we extend our understanding into solving two material composite members. Okay, and now we learn how to define the stress state when the eccentric load is applied. So we simply combine our knowledge about axial loading, and pure bending. And then we define the total stress state by superposing the stresses for individual loads. Okay, that's it. And then you have a homework based on what we have learned so far. Or torsion. Yeah, only on torsion, right? Yeah, only on torsion. So I hope that you can complete it and submit by this deadline. Okay, so that is the end of the section on pure bending. And before I give you a break and start the new topic, I would like to do a few questions with you from the exercises that I have uploaded into the Moodle course site, so that we can consolidate what we have learned so far. Okay, see if we can apply them and solve some problems. So could you now go to the Moodle course site and get the exercises for pure bending? Okay, this document. So I'll give you a few minutes to get ready. Altogether, there are 6 questions. Yes, I may not have time to complete all the questions with you now. Okay, so in the tutorial class, I will work out some questions with you. Simple questions, I'll leave that one for you. Try by yourself, and I will upload a solution for you to check your answer. Okay, simply because you have the solution, don't stop working on these questions. Make mistakes by doing it by yourself. Okay. Okay, so I hope that you are now ready with this exercise, and there's no point of simply listening to me now, right? You need to write down. You have to use your hand and write down, work with me, and try to understand the logic, the logical process that I'm going to go through to solve this problem. Okay, so if you get that logic right, then you can solve any kind of problem. And one important thing, you need to write down all the steps. Whenever you use an equation, first thing you should do is to write the equation in symbolic form without substituting the numbers, right? When I mark your assignment, I'm seeing that you simply put the numbers into the equation and show me this is the equation, but there's no equation there, only numbers, meaningless. Okay, so if you do that kind of thing, I'll deduct some marks, because I have told these things several times now. First, write your equation in symbolic form and then substitute the numbers. Okay, right. So shall we read the question first together and try to understand this one? It says, knowing that the couple shown acts in a vertical plane, determine the stress at point A. So point A is in here, and point B here. Okay, first understand the problem. Now, this is actually a pure bending case where there's a cantilevered beam. So this cantilever beam is attached to the rigid body here, a wall. Okay, and it's a hollow section. How do I know it is a hollow section? Yeah, by looking at, you can tell that one, right? There's a dotted line of drawn inside showing the internal cavity. So here is a, what is given to the left is the cross section. Okay, it's a kind of a magnified diagram, and there, this is where the material is. Middle part is hollow. Okay, like this. Middle part is hollow. Okay, so now you need to find out the stress at point A and point B. So since it is a pure bending case, there are going to be a neutral axis here, right? So first thing, you need to locate that neutral axis. So since it is a rectangular shape, it has two symmetric sections, more than two. Therefore, once you draw the two symmetric axes, then you can find out the neutral axis. So it is right at the middle. So if I extend it like this, so this is the neutral axis, N A. So I can say here N A. Yeah, that is the neutral axis. All right. So now you can find out the distance to the neutral axis and also distance to point A. So this point A is, let's say, YA from the neutral axis. And point B here, we'll mark it as YB from the neutral axis, because we need that information, right? And now if you want to find out the stress at that given point A, we use our bending formula here. Sigma is equal to negative my I. So if the stress at A is sigma A, it should be negative M, same M, okay, YA over I. And then sigma B should be negative M YB over I. Okay. So we can find out this YA and YB because we located our centroid at here. See. So what are the unknowns here or knowns? We know M, we know YA here. So only unknown is I. Here again, these two, only unknown is I. So once you find the I value here, moment of inertia, we can solve this problem. Okay. So how to find out the I of this hollow section? Some of you already learned this thing, so it may be very simple for you, but others who have not learned it before, now carefully listen to me, right? So I'm going to draw a figure here to show the cross section. This is the cross section, and let's take the moment of inertia of this section as I. Okay, and here is the neutral axis. Extend it a little bit, and then I'm going to draw this is equal, we can say that this one is made of a bigger cross section in the rectangle like this, and then you subtract this one, the inner part, this one. Then you get the bigger cross section, the hollow cross section, right? So if you know the moment of inertia of this one about its neutral axis and moment of inertia of this one about its neutral axis, then I of the total section is equal to I1 minus I2. So this is how we find the I. And all are 1 and 2 are rectangular sections. Therefore, for rectangular sections, we know that I is given by 1 over 12 BH cube. So this is another information that we need here. So knowing those two, how to find out I and the I of one section, now we can find out the I of the total section, right? So therefore, I is equal to, I would write this way, 1 over 12, is right, B1 H1 power 3 minus 1 over 12 B2 H2 to the power 3. Okay, so shall we substitute the numbers here now? 1 over 12 B1 is given as 40, 20, 20, 80, right? It is 80, all 9 millimeters. And H, 80, 20, 100, 120, 120 to the power 3 minus 1 over 12 B2. B2 is the inner part with 40 and the height is 80 to the power 3. Okay, now you simplify this one, you can get the answer. I will write my answer here directly. 9.81333 into 10 power minus 6 meters to the power 4. Okay, now the rest is easy, right? So you get the part A there. Sigma A is equal to negative m y a over I, and here y a, how much? What the size of that? Y a is 40, right? 40 millimeters. Okay, so therefore it is equal to m is 15 kilonewton meter. 15 into 10 power 3. Ya is 0.04 meters divided by I. We find that 9.81333 into 10 power minus 6. You simplify this one, you get the answer given. It is you get a negative answer, right? It is negative 61.6 megapascal compressive stress on the top. Is correct, right? So the way the load is applied, here it is tension, here it is compression. So can you do the B? So I think I don't need to do the B for you. You can do it. To M Y B over I. Yeah. Y B. What is the size of the Y B? 40 plus 20, right? 60 millimeters. Okay, the rest you will do. Okay, you get the answer. So answer is given to you. So check the answer. I don't need to spend my time here for that part. Right. Next, let's look at the question number 2. Question number 2 is very similar to the one that we have done. Right. Only thing is you need to know how to find out the I of this section. So there are different ways of finding I. One way is to define it as a bigger rectangle, okay, and then subtract side and also the other side like this. Then you get a I like this. Okay, so that's one method. The other method is to cut this member or take it as 3 rectangles like this. 3 rectangles, and then you can find out I by adding the I about neutral axis for these 3 sections separately. Okay, so I think I will leave that one for you. I will do one more difficult question. So let's read this question. It says 2 vertical forces are applied to a beam of the cross section shown. A to D is a beam and the transverse loads are applied at point B and C, 10 kilonewton each. Determine the maximum tensile and compressive stresses in portion BC of the beam. Why portion BC? Because portion BC is now under pure bending. Internally, from B to C, there's only one internal moment. But from A to B, internally, there are 2 loads. So still we didn't learn how to solve that kind of problems. Okay, so therefore, B to C is our focus area. Now there, the cross section shape is given. It's a U-shaped cross section. What we need to find out, determine the maximum tensile and compressive stresses. So by observation, you can say that. Now I don't need to tell this one now. You should be able to, right? This side is now under compression. This side is under tension. By visualization, you can visualize in the way it is going to bend. You can tell that. Okay, to how to find out the stress, compression, and tension. Again, the same formula, bending formula. Sigma is equal to negative my I. This is the equation. And there we need to find out this M, that is the internal moment M. Internal moment here is equal to externally applied moment as well, because it's a pure bending case. Why? Yeah, to find out the why, we need to locate the centroid of this section. I don't know why. I also don't know. So all three we need to find out. Okay. So first we'll try to locate the centroid. So once you locate the centroid, we can write the value of I easily. Okay. So for U section, where the centroid, we'll just assume that it is going to bend about its neutral axis. Neutral axis is here, NA. I don't know exactly where it is, but I just mark as that. And then the distance from the bottom up to the neutral axis, Y bar. Okay, so this is what I'm going to find out. You can write an equation and find this one out, or you can use the tabular method that I have introduced in the class, and then use that method to solve this problem or find out the neutral axis or the distance to the neutral axis or the centroid. Okay, right. So let me draw this U-shaped section as three rectangles, and then using those three rectangles, I'm going to find out value of Y bar. Okay, so let me draw that section just like this. Okay, and then I'm going to mark this one as 1, this one as 2, and this one as 3. 3 sections. Okay, my target is to find out the distance to the centroid. Centroid going to, our neutral axis is going to go through the centroid. Okay, the distance to the neutral axis or the centroid, Y bar of the section. Okay, and just to tell you that here sigma, my negative my over I should be about the neutral axis all the time. Okay, that is why what we need to find out now, I above the neutral axis. Now we are locating the neutral axis first. Okay, how to find this one? We need to know the distance to the centroid of each section 1, 2, and 3. So the centroid of this section is going to be right at the middle. Therefore, I mark it as Y1 bar. And here is the same height. Let's mark it as Y2 bar. And here also at the middle, and that distance I marked as Y3 bar. Okay, and then let's use the tabular method to find out the Y bar. So there, first you need to draw a simple table like this, and there I'm going to write down first the area of each section, and then I'm going to write down the Y bar distance, and then I get the multiplication of the Y bar and A. So first the cross-sectional area in millimeters squared, and then Y bar in millimeters, and then I will find out A Y bar quantity. It is in millimeter to the power 3. Okay, I will denote the 3 section by 1, 2, 3 numbers, and 1 is the section 1, and the area here is 10 into total height is 60, right? So A1 is equal to 10 into 60. That is 600 millimeters squared. How about 2? 2 is the same, therefore it is also 600. 3 is height is 10 and the width is 30. Right? This is A2. A3 is 10 into 30, 300. Okay, right. And next, Y1 bar. Y1 bar, height divided by 2, height is 60, therefore it is 30. And Y2 bar also 30. And Y3 bar, height is 10 divided by 2, 5 millimeters. And now I get the multiplication. 30 into 600, I did the calculation, it is 18 into 10 to the power 3. And here 18 into 10 to the power 3. And this one is 1.5 into 10 to the power 3. Now I'm going to find out the summation of all the area. Right? So that value is 1500 millimeters squared. And also I'm going to get summation of all the AYs. It is equal to 37. 37.5 into 10 to the power 3. Okay, so now our equation for Y bar is equal to summation of A Y bars divided by summation of all the forces areas. So this is the equation. So from this one we find that 37.5 into 10 to the power 3 divided by 1500, and you simplify this one, you get this answer, 25 millimeters. So we found that Y bar here is 25 millimeters. So knowing that, now you can find out the I about the neutral axis. So how to find out the I about the neutral axis? Okay, so to find out the I about the neutral axis, we can take the I of each section about the neutral axis and add them together. But again, you can see that what we normally can write I of its own centroid, about its own centroid. Okay, so we need the parallel axis theorem here to write down the I about the neutral axis. So let me just write the total equation. What I need to find out is I about the neutral axis. So this one is equal to I1 about the neutral axis. That is the, if you take the section 1 and take the I of that section about the neutral axis, okay, plus I2 about the neutral axis plus I3 about the neutral axis. So what is the I1 about neutral axis? 1 neutral about the neutral axis. Can you write that one? From the parallel axis theorem. Maybe I write the parallel axis theorem somewhere here. Parallel axis theorem. If you can remember, it is equal to I is equal to I bar plus AD squared. So this is what the parallel axis theorem says. Okay, I bar is the moment of inertia about its own centroidal axis. Right, D is the distance between the centroid and the neutral axis. So now that way I can write my I1 about neutral axis. It is equal to 1 over 12 B1 H1 cube. That is the I bar. This is I bar. Okay, about its own neutral axis, about its own centroidal axis. Then plus A1 and D1 squared. Okay, so we'll find substitute the numbers. 1 over 12 times B1 is the width of section 1. It is 10 millimeters, right? 0.01 in meters, or we'll write everything in millimeters, later convert into meters. 10 millimeters into height. Height is 60, right? 60 to the power 3. Then the area A1, we calculated it as 600. 600, okay? And then the D1, what is D1? Here, D1 is, let me mark here, D1 is this distance, D1. Distance between its own centroidal axis and the neutral axis. So what is the distance? 30 minus 25, right? 5 millimeters squared of that, right? How you get this D1? This is equal to 30, that is the half the height of that section, minus Y bar 25. Okay, right. You simplify this one, then you can get this answer. It is 195 into 10 power 3 millimeters to the power 4, right? And here we know that I1 and I2 are the same. Therefore, I can simply write I1 about the neutral axis is equal to I2 about the neutral axis. So then I need to find out I3 only. Can you write the equation for I3? So now I directly write that one here. 1 over 12 B3 H3 cube plus A3 D3 squared. 1 over 12 B3 is now section B3, the bottom part. This distance is the B3. B3. So that B3 is equal to 30. Okay. 30. And the height 10 millimeters to the power 3 plus A3 is 300 into D3. So D3 is equal to Y. Can you locate that one here? So I just extend this one. This is the D3. That is 25 minus 5, that is 20 millimeters. Okay, so you substitute that number here, 20 millimeters squared. So you simplify this one, I got the answer as 122.5 into 10 to the power 3 millimeters to the power 4. Okay, right. And now it's simple now, because I found out the value of the I, total value of the I, by adding them together. So I and A is equal to 195 times 10 power 3 plus 195 into 10 power 3 plus 122.5 into 10 power 3. Answer I got is 512.5 into 10 to the power minus 9. This should be in meters to the power 4. I converted into meters as well. Okay, right. And next, I need the value of M. How to find out the value of M? So to find out the M, we need to cut this member between A and C somewhere here and draw a free body diagram. So let me cut this one at this point. Let me mark it as XX and draw a free body diagram for A to X. Okay, so I'm just drawing the free body diagram from A to X, A to X, like this. And then I have this force applied here, P. It is equal to 10 kilonewton. Okay, and from the way the loads are applied, 10, 10, equally distributed, mean the symmetrically applied. Therefore, this force here also should be equal to P, 10 kilonewton, right? And then there should be a internal moment M. That is what we need to find out. So we'll mark the distances as well. We need that one. So this distance here is the half, no, 150 millimeters, right? So I mark it as A. It is equal to 150 millimeters. And the distance to the cut point here, this distance marked as X. Okay, so now I can simply write my equation of equilibrium. I take the moment at X, this is X, okay, summation of M at X in this direction equal to 0. So can you write the equation in the symbolic form first? Is equal to M in that same direction, positive direction, and then I take the P, first P is also in the same direction, create the moment P into this distance. That distance is equal to X minus A, X minus A, and support P going to create a clockwise moment, therefore it is negative P into the distance X is equal to 0. So once you simplify this one, you find that M is equal to P times A, because Px minus Px cancels off. Okay, so now we know the value of M. So now it is a matter of substitute the numbers, right? Sigma, we want to find out the top. Or sigma, yeah, on the top it is a compressive force, right? Stress, sigma top is equal to negative M. I write Y top divided by I and A. So M is equal to P into A. P, we know the value of P, right? So if you want, we can write P is 10 kilonewton into 10 power 3 into A is 150, that is 0.15. So if you simplify this one, you get that it's equal to 1.5 into 10 to the power 3 Newton meter. So now substitute the numbers, 1.5 negative into 10 power 3 into Y top. What is Y top? Y top, that is the distance from the neutral axis to the top surface. That is this distance. This is Y top. Total is 60. 60 minus 25. So that is 35 millimeters. Similarly, we'll mark the Y bottom as well. Oh, Y bottom is Y bar, so we don't need to mark that. Okay. So Y top is 35,035 divided by INA. We found that is 512.5 into 10 power minus 9. So you simplify, you get the answer negative 104, 102. 102.4 megapascal. Answer is given. So I'll leave the next part for you. Sigma bottom. Find out this one is equal to m y bottom divided by I n a, and see whether you can get the same answer given here, 73.2 megapascal. Okay, right. Let's have a short break. So now it's 11 past 5. So we'll start at 20 past 5. So now you can ask any questions if you have, or we just have a short break. And once we come back, I will do the new topic. Okay, that is about the design of beams for bending. Okay, so maybe at this point I will answer that question somebody asked about final year project. In one group, 3 members, yes. Okay, every final year project group, number of members in a group is 3. So find 3 members. Okay, so later, once we give the project list, you can select projects from that list, or you can propose as well your own ones. Yeah, so very soon we will send you the list of projects. Very soon, in the sense it will take at least 1 month, because at this moment we are collecting all the proposals from the industry and also from our own academic staff. Okay, then we will publish those available proposals from our side in the Moodle course site. Okay, then you can select up to 10 projects and inform us in the order of preference from 1 to 10. Okay, we will give you a submission link, and then you are going to submit into that link. And if you think that you want to do your own project, you can propose your own project too, right? So when you propose your own project, it is always going to be your number 1 choice, right? If you propose your own project, still you need to select 10 other projects from the available list, because sometimes the project that you propose by yourself may not be suitable for final year project. Okay, your final year project coordinator will go through your proposal and then decide whether it is suitable or not. In case if it is not suitable, still you have another 10 list, right? The 10 projects listed. So therefore we will assign you one from that selected 10. How to select the one that you want? Again, we need to have a fair mechanism. There, what we do, we are going to create a priority list, right? Priority list for each cohort, for your group. That priority list we decide based on your GPA of the first semester. Okay, because by the time we make the project allocation, if we have your second semester GPA, we are going to use that one as well together. Otherwise, we use your first semester GPA and find out the average GPA of your whole group, 3 members average GPA, and create a number. Using that number, we are going to create the priority list. A group having the highest average GPA have the first priority to select a project. So your list of 10 projects, the first one will be assigned to you. Okay, the second in the list, if your first one is not taken by the first group, then you will get your first choice, something like that. Okay, so from our previous experience, we know that majority of you get a project within your first 3 choice. You have to wait. Somebody asked, what are the topics about? So you have to wait for the topics. Normally, 2 types of projects. One category is more research biased. The other category is more design biased. But all the projects will has some kind of design elements, and also there are some research elements combined together. But some projects can be more research bias, the other one may be more design bias. That's what I can say at the moment. And later, once we prepare the list, you can see a range of projects depending on your preferences. You can select the one that you want, or you have to discuss your team with your teammates, right? So when you are forming a group, make sure that you find equal-minded people, right? So that you can find a common topic for interested for all of you. Okay. So now here, one way of forming a group. Now, if you have selected your elective subjects more in the, let's say, MSE area, right? We have our mechanical services and environmental engineering group. And if you selected more your elective subjects in that area, select 3 members who are interested in similar subjects. Okay. And if you have selected subjects in aircraft area, then find out 3 members in the same area. But it is not a must. If you select that way, then you can see that everybody is, having similar interest. But it is not a must. Our project coordinator will give you more details later, a briefing session. So for that briefing session, everybody should come. If somebody not come, that means he is not suitable to graduate next year. Because the final year project is a key component. Even Hong Kong IE, they check your final year project, your grade. When you go for your professional interview, they will look at that. Because final year project make you an engineer who can take responsibility, who can take decisions by yourself, and who can successfully complete a project by yourself. Your supervisor is going to be a consultant only. He will not help you to complete the project for you. Right? You do your project. You set the direction. You get the advice from your supervisor. So if you happen to get a chance to meet your senior year students, talk to them. Now they are doing their experiments, design work, prototyping in the labs. You can see how they work. Okay, let's start again. Now you need to have your lecture note for the new topic, that is about forces and moments. All right. Hope that you have your lecture note with you. So we are still in the bending. The section on bending is quite long because bending covers many topics. So I'm going to spend 5 weeks with you. So this is going to be the second week, right? 3 more weeks to go. All right. So today's lesson on this topic, the focus is to find out the internal forces and internal moments. So in the pure bending case, we learned that there's only one internal load. There is a moment, right? We call it a bending moment because it creates a bending, and it creates by applying moment coupled from the two ends of the beam. But most of the time, what you find as beams, the loads are applied in the transverse direction. That is not along the major axis, but perpendicular to that. So like shown in here, in this diagram, like this. So here you can see a simply supported beam. You heard this word before, right? And then a distributed load is applied over that. And the distributed load is applied in the transverse direction, perpendicular to the beam. Beams are normally long compared with its cross section. Cross section is small, lengthwise it is long, right? And they are subject to different kinds of loads as well. It may not be only transverse loads, okay? And also it may not be only distributed load. There can be concentrated loads as well. So once you cut open this member at any point between the load application points, and then draw a free body diagram. So then you see your reaction force and then the externally applied distributed load is, and this is the point A, and I just cut at X, and then internally you see two forces. I will explain a little bit more later. One is a shear force, denoted by V, and the other one is bending moment, M, two internal resistive loads. So the values of these shear force and the bending moment is not constant. It's going to vary along the member A to B. So when it comes to designing this member, we need to know where the maximum stress is. We know that maximum stress is going to happen in the outer surface of this beam, right? But at what location along AB? We have to decide that by finding out the maximum values of shear force and shear bending moment, V and M. So since V and M is not a constant, it varies along the length of the beam. Now we need to find out the shear force variation along the beam and bending moment variation along the beam, right? So what you can see here in the the figures given, this is the shear force diagram, how the shear force vary along the beam. And the bottom one is the bending moment diagram, and it shows how the bending moment vary, that is M, vary along the beam. So by visualizing this, drawing the distribution of stress, so for the force, shear force and the bending moment, we can find out the locations which are called critical locations. Now we know that bending moment is maximum at the middle of this beam, and the shear force is maximum at the two ends, at here and here. So if this one going to fail by shear, it's going to fail at A and B. If this is going to fail due to bending moment M, it should fail at the middle, right? Now this is easy, but how about a like aircraft wing? Aircraft wing is a member subjected to bending. A lot of different loads applied here, and it's a beam. And every member here is subjected to different kinds of transverse loads. So we are how to find out the maximum, the point where the maximum stress is or maximum forces are, right? For that, you need to have good knowledge about uh, the forces and moments, internal force and internal moment generation along the member. So that is what we are going to learn here. Okay, so I hope that I have positioned the requirement or the knowledge that you need to have here to solve right kind of problems. Okay, so this is the outline. So how I'm going to uh, introduce this topic, I'm first going to talk about different kinds of beams and different kinds of loading that we expect in a beam. So it covers almost all the type of loads that you expect in industrial application. Okay, and then I will show you how to draw a shear force diagram and a bending moment diagram. Okay, the shear force and the bending moment, those are internal shear force and internal bending moment. They are due to the externally applied loads, right? So they are resistive forces. Therefore, externally applied load, shear force, and the bending moment, all three are interrelated. So I'm going to show you that relationship. Okay, because the shear force and bending moment diagram construction method that I'm going to introduce to you today is the fundamental approach, very basic. So with that method, you can draw a shear force or bending moment diagram for simple problem cases. Complicated problems like in the aircraft wing, if you use that method, it takes long time to complete the problem. For that, we use fast methods. Fast methods you can use once you build up your fundamentals. So that is why first I'm going to introduce you fundamentals, right? After that, I will introduce this relationship between loads, shear force, and the bending moment. And then I will teach you a faster method of constructing those diagrams for complicated problems. Okay. And lastly, with that knowledge, I will teach you how to design a beam. Okay, that's the plan. So I will do the first two today, remaining two next week. So let me go a little faster now. Okay, so I don't need to explain again what a beam is. Beam generally subjected to transverse loads, different kinds of loads, but it is not how a beam is defined. Beam is defined based on the internally generated loads. A member which generate internal bending moment is called a beam. Okay, so we need to design it to resist that bending moment, support that bending moment. And kind of loads applied on a beam, there can be concentrated loads or distributed loads. So these are concentrated loads, right? And these are distributed loads. The distributed load can be uniformly distributed or non-uniformly distributed. Okay, so there are different kinds of distributions of loads as well. And as I showed you before, if you take a beam, now here you can see a cantilevered beam where one side is fixed and the other end is subjected to a transverse load P. Now in this member, from A to B, at any point, if you cut the member and open up, you will see internally two forces. One is this shear force, right? V. And I mark this shear force direction strategically. I will tell you why I mark it that direction. Okay. And the bending moment M is to resist the couple created by P and V together, create the couple, right? So we need to apply this bending moment to counter that. So this shear force V and bending moment M, I told you it vary from along the length A to B, right? So when you are designing a beam, the first thing is to find out where the maximum force, where the maximum bending moment, right? So therefore, the first thing that we do in a beam design, In fact, there are two steps. The first step is to determine the internal shear force and internal bending moment. Okay, that will help us to find out the places where the maximum shear force and the maximum bending moment. So this is the first step. Draw two diagrams like this and locate the place where the maximum forces. And secondly, you are going to select a right material and right cross-sectional shape to support that load. So that is the second step. So then you look at the standard cross-sectional beam, not the beam, okay, I can say structural members, structural steel or structural metals available, and then select the right one for your application. Okay, so that is the basic design approach. And when it comes to beams, there are different kinds of beams. The first one in here, we call it a simply supported beam. It is supported at two ends, and the load is applied anywhere, transverse load along the length. And this kind of second B type beams are called overhang beams. Now, this part is the overhang without any support, right? The second support is not at the end, and the load may be applied somewhere here or maybe here, like that. And then we have a cantilever beam. Now we just learned cantilever beam. It can be distributed load applied like this, or point load applied like this. Okay, like that. And then sometimes these kind of beams are called statically determinate, because the internal the resistive force, sorry, reaction forces at the support can be found using only equation of equilibriums. And some beams are categorized as statically indeterminate. The reason because they contain more supports than necessary to keep the beam in equilibrium. For example, this one is basically a simply supported beam, right? But it has additional support, which is not necessary to keep it in equilibrium. So whenever you introduce this additional support here, we are going to have a situation where there are more unknowns than the number of equations we can write to solve the problem. So then it becomes statically indeterminate. So the rest, I think you can understand, so I'm not going to spend time on that. Okay. So when designing a beam, the first thing that we need to know is what is the maximum stress and what the nature of that stress. Is it a shear stress or a normal stress? So for beam, most dominant stress that we need to pay attention to is the normal stress or axial stress due to bending moment. There's a shear force, right? Like this shear force. But that shear force is not that critical. The failure we can avoid easily. For this shear failure, we can easily avoid. Shear force can be critical in certain situation, but normally it is not the critical failure mode. The bending beams going to fail mainly because of the axial stress caused by the bending moment. We learned in the pure bending case, right? Bending moment creates a linear distribution across the cross section, right? So if you find out the neutral axis, we know how the distribution is, something like this, right? Stress in the axial direction, right? Tension or compression, axial stresses or axial forces. And we know how to find out that axial stress using bending formula. Sigma x equal to negative my I. And if you want to find out the maximum values, we simply replace y by c and then use this equation. Okay. Or another modification of that equation is using the section modulus. Here S is equal to R over C. This is okay. Right. So now to design this member, we are going to find out the maximum stress using bending formula. For that, we need to find out the maximum bending stress, bending moment, right? Since bending moment and shear force is interrelated, we are going to draw both shear force diagram and bending moment diagram, or the shear force distribution along the member and bending moment distribution along the member. And then we can visualize where the maximum values are. So that is what I'm going to introduce you today, how to draw those shear force diagrams and bending moment diagrams. Before I move forward, let me introduce your sign convention here, which will be very useful. Okay. The first step when you are designing a beam or calculating the maximum stress in a beam, we first start with our what you call physical diagram, right? Or we call state physical diagram, how it going to be look like in the real environment. And then by looking at that, we are going to draw a free body diagram. This is FBD. Okay, free body diagram shows you all the externally applied loads, including the reactive forces. Okay, so that helps you to find out unknown reaction forces. These RA and RP are unknown reaction forces. Okay, and then to construct the shear force diagram and bending moment diagram, we need to find out the internal shear force, internal bending moment. So that means we need to cut this beam at different locations and find out the shear force function and the bending moment function, because it's a variable, right? It varies. So we can define it as a function. Right? So just to avoid any confusion when you write the equations, you need to know the sign convention. Here we define a positive shear force as a shear force, internal shear force, that create a clockwise rotation in the beam. So what do you mean by a clockwise? Now you can see here is clockwise rotation, right? Like this. A beam portion which is subject to clockwise rotation. So how you see the clockwise rotation? Now I'm going to mark the shear force while cutting the the beam at C and in here. And this is the shear force V. I mark it in downward direction here. So now you look at the AC portion of this beam and forget about the P1 and the distributed load and also M. Apply only V, right? Once you apply only V, the beam is portion AC going to rotate about A, about its support, right? In what direction? In this direction. So it is clockwise or anti-clockwise? It is clockwise. So it's a clockwise rotation. Therefore, this is a positive V. That is the reason why I mark it downwards. Okay, so always unknown forces you mark in the clock positive direction. So then by looking at the answer, we can decide whether our marked direction is correct or not. Okay, and look at the same or the other portion of this beam, CB. CB, now if I mark the shear force there, I should mark it upwards, right? And the V prime here should be equal to the V. So that way, once you put them together, there's no internal force. I mean, they cancel off. You cannot see them. Okay, so now again, look at the beam section CB and forget about all the other loads and keep only the reaction force at B. Then apply the shear force V prime upwards. So then how this beam section CB going to rotate? About B, it is going to rotate in this direction. So is it clockwise or anti-clockwise? It is clockwise, right? So therefore, this V prime I marked here also positive. Okay, can you see that now? So a positive shear force creates a clockwise rotation in the beam portion. That is how we define positive shear force. Now look at the bending moment. It says a positive bending moment, internal bending moment, okay, is the one that creates tension at the bottom or lower side of the beam. Tension at the bottom. So now here you can see that this side is tension, under tension. So if you apply the bending moment in this fashion, it creates a tension at the bottom. So that kind of bending moment is called positive bending moment. So now look at this bending moment in here. I mark it in a different color. Now let me take another color. Okay, like this one. So once we apply this bending moment to beam portion AC, what is going to happen to this section AC? Again, keep the support at A. So then this beam going to bend like this, right? So that means in the bottom side, we are going to create tension. So therefore, this is a positive bending moment. Look at the opposite section, CB. There again, I mark my moment in the opposite direction. Okay, and the magnitude of M prime is equal to M. So again, you can see that you apply only M prime and see what is going to happen to CB. CB going to bend like this, right? So again, it is a tension at the bottom, therefore positive bending moment. Okay, so now if you refer to this diagram in here, we can see this is how we mark the positive internal shear force and internal bending moment. Right. The corresponding external loads are given in here in these two diagrams, but no need to pay much attention to that, okay, because we are going to look at internal ones. Okay, so with that understanding about this, the sign convention, now let's look at how a shear force and bending moment diagram is generated, developed for a simple case. Now, those who have learned this one before, you might find that's nothing new, right? But I know that there are some students here, they have not learned this kind of thing before. Therefore, let me explain for the benefit of them, okay? So for you guys, it can be a revision. Okay, so now here what we can see is a simply supported beam with a middle load P, okay? The first step is to have our physical system, and the second step is to draw a free body diagram. So I have drawn the FBD and marked the reaction force RA and RB. Okay, since the load is right at the middle, therefore support A and B equally share the load. Therefore, size is equal to P by 2. RA is equal to P by 2. RB is equal to P by 2, same. So now I don't need to really write my equation of equilibrium to find out the reaction forces because it is very obvious. But if the load is applied, let's say not there at the middle, shifted towards one end, then A and B will not provide the same reaction. So you need to find out the reaction force by applying equation of equilibrium. Okay. Now, from A to D here, A before just before D, no other forces, right? From A to D, at A there's an external force, reaction force. At D, external force. But between A and D, there are no other externally applied loads. Therefore, we expect the shear force and the bending moment is continuous from A to D. We can define the variation of shear force and bending moment using a one function. But at D, since a new load come in there, shear force and bending moment going to change suddenly. Okay, so here the load application points are called the discontinuities, because at that point suddenly there's a sudden change of shear force, sudden change of bending moment. Okay, so load application points are called the discontinuities. I write the word, okay, discontinuity, right? So here in this diagram there are three discontinuities at A, and then at D, and at B. There are three discontinuities. Okay, so between AD and DB, the variation of those shear forces and bending moments going to be somewhat continuous. Therefore, in order to define this shear force and bending moment variation, we need to write shear force function and the bending moment function from A to D first. Next, D to B. Okay, to find out the shear force function, bending moment function from A to D, we need to open up the beam between A to D and find out the function for internal force and the internal shear force and the bending moment. So for that, what I did, I'm going to cut this beam at C and draw the freeboard diagram for cut portions. So that is what is given next. Third step. Okay. So once we cut the beam at C, we have to now mark our internal forces. You can see that I mark internal shear force in the positive direction, internal bending moment also in positive direction. The other side also opposite direction, but they are also positive. Okay, now let's find out a function for this V and M. For that, we can apply our equation of equilibrium and find out the value of V. For V, what we have to do, we simply write our equation of equilibrium for in the y direction. All the forces in y direction, Fy, should be 0, right? So now this is for AC. Okay, I'm writing for AC. I cut the distance to C is x. So that means RA. So RA minus V should be equal to 0. Right. So this one says that V should be equal to RA. RA is equal to P by 2. So that is how we get this one. So that means that shear force is a constant value from A to C, because there's no variable x come in this equation. It is constant. Okay, right. And then how about the bending moment? To find out the bending moment M, we need to apply again moment equation of equilibrium for moment at point C. Summation of all the moments at C should be equal to 0. So that means now I'm writing the equation directly. See whether you can write this one by yourself. M, and then we will not come to the equation. RA will create a negative bending moment, right? RA into X equal to 0. So that means M is equal to RA, that is P by 2 times X, Px over 2. So that is how I got this one. Two equations. One is for bending moment, the other one is for shear force. So bending moment equation is a function of X, linear function. That means when X equal to 0, bending moment is 0. So that I want to mark in this diagram here. M is X equal to 0, bending moment is 0. When X is equal to L by 2, because this equation is valid from A to D only, because we write this equation for A to D section, right? When X is equal to L by 2, M is equal to PL by 4, PL by 4. Okay, so this is the point. So in between, variation is linear. So I can construct my bending moment diagram. This is the BM bending moment diagram. Okay, from A to D, and the shear force when X is constant, right? From A to D. So value is P by 2, and after L by 2 also P by 2. So this is the shear force from A to D. And then to find out the shear force and the bending moment from D to B, we need to cut this member again from any point from D to B. So I cut it at E and draw the freeboard diagram for cut portion AE and DB. So this is my FBD, okay, and this is my FBD as well. And there again, I'm going to mark my shear force at the cut point in the positive direction and bending moment in the positive direction too. And from the EB also same thing, right? So now I'm going to find out. Oh, next thing is I will mark my position E, the distance to E as X. This cut portion. And always, I forgot to mention, before you start working on a beam problem, you need to define your coordinate system. So here I'm going to define my origin at point A, and this way I measure Y, and this way I measure X. All the time, measurement takes from the origin. Okay. So now, again, for cuts portion A to E, you can write your equation of equilibrium, but it is easy to write equation of equilibrium from E to B because not many forces, right? Both sides are okay for equilibrium. So I'm going to write from A to, sorry, not A, E to B. From E to B, apply again equation of equilibrium. So there, I'm going to take the positive moment as this way, and then apply my moment of, sorry, equation of equilibrium in y direction, Fy equals 0. So that means V prime, or it's equal to V. Okay, maybe I can remove the V prime. V plus RB equal to 0. Okay, if you simplify this one, we get V is equal to negative RB. RB is equal to P by 2. That means this equation. V is equal to negative P by 2. Similarly, now I can apply my equation of equilibrium for moment at point E. This way, summation of all the moment at E should be equal to 0. Right. So there's M, but it is in the negative direction, therefore negative M, and RB creates a moment in the positive direction, therefore positive RB times the distance. What is the distance? L minus X. L minus X. This should be equal to 0. Okay, you simplify this one, then you find that RB is equal to P by 2, M is equal to positive P times L minus X divided by 2. Again, V is a constant, negative P by 2, and the moment is a function of X, right? So here, let's take the V, and when the V is L by 2, negative P by 2, and at the end also same value. So this is the shear force diagram variation. So at the point T, there's a sudden jump from positive to negative. And how about the bending moment? When X is equal to L by 2, you substitute here x is equal to L by 2. What's going to happen to m? M is equal to L by 2. Is can find out the value is equal to PL over 4. So that means this point. When x equal to 0, so not 0, x equal to L, m become 0. So this point. So then D to E variation is like this, right? So now we constructed the bending moment diagram. This is the area under the bending moment diagram. This is the shear force diagram. So this is the area under the shear force diagram. Okay. So this is how we construct shear force diagram and bending moment diagram. So this is a very simple problem. My purpose here is to introduce you the fundamentals. So if you get these fundamentals in your head, now you can do any problem easily. Right? Whenever you get stuck, come back to the fundamentals, then you can see the way forward. Right. So with that introduction, let's now work on a problem so that we can apply the knowledge and solve this problem. So what it says, draw the shear and bending moment diagrams for the beam and loading shown. So it's a different kinds of beam, and it's an overhang beam, right? The loads are up to, there are two external loads. So by looking at this one, first thing that you normally do is to draw a free body diagram. Okay, free body diagram. So once you draw the free body diagram, you can see that there are two unknowns, that is the reaction forces at P and D. So you should be able to find out the reaction force using equation of equilibriums. Okay, and then we need to find out the internal shear force and internal bending moment to construct the diagrams. Okay, so the first thing that you need to learn, know to find out the shear force and the bending moment function is to identify how many discontinuities in this bending moment, in this beam. So discontinuities are the point of load applications. So at the point of load application, there are going to be sudden change in bending moment diagram or shear force diagram. Now here point A is a discontinuity. Point B going to be discontinuity once you find the reaction force. C is a discontinuity. D also discontinuity. So from A to B, shear force and the bending moment going to vary uniformly, right? Continuously. I can't say uniform, continuously. B to C also the same. C to D the same. Therefore, to solve this problem, to draw the free body bending moment diagram and the shear force diagram, we need to cut this beam at 3 locations, from A to B first. Okay, here, and then B to C, and C to D 3 times, and then write the functions for shear force and bending moment. So once you do that, you can construct your shear force and bending moment diagram. But you don't need to do this thing later, because once you learn the basics, we can find out easy method of constructing bending moment diagram and shear force diagram. But I want you to now use the fundamentals. Okay, let's start working on this one. The first step is to draw a free body diagram. Okay, so what I'm going to draw here now is the FBD. FBD. So it is not the FBD, so I'm going to draw the FBD here by drawing the shear force, or sorry, reaction forces. Okay, and then identify this reaction force as RB and this one as RD. Okay, and then now you find out RP and RD by writing the equation of equilibrium for the whole beam. To find out D, sorry, RB, we can take the moment around D. Now this time, from the way the equation is written, I can see that I'm writing the equation taking the bending moment as positive in this direction, clockwise direction. Okay, so can you write the equation and see how it is written? First I take RB. RB create the positive direction moment, therefore positive RB, and the distance to the RB is 5 from D. Okay, and next I take 20 kilonewton. 20 kilonewton creates anti-clockwise moment. According to my definition, it is negative, therefore negative. 20 into the distance to that point, 5 plus 2.5, 7.5. And 40 creates again the anti-clockwise, that is negative here. 40 into distance 2. That's complete the equation. It is equal to 0. And then I can find the RB. You can do the same thing for apply the same equation in clockwise or anti-clockwise direction as positive. Then you can find out RD, 14 kilonewton. Okay, next I'm going to open up the internal shear force, internal loads. So therefore, I'm going to cut this beam first at point 1 here. Okay, and draw the freeboard diagram for the cut portion A1. So this is A and this is 1, A up to 1. So here we can see that internal force V1 is marked downwards like this. You guys can hear me, right? Still, I hope that still you can hear. And then bending moment also marked in the positive direction in this way, M1. Okay, now you just write the moment equation of equilibrium in positive y direction this way for that A up to 1. Then we say that there's negative downward is negative 20, negative V1 is equal to 0, then V1 is negative 20. Is the function of the shear force. Bending moment, we'll take the moment around 1 in this direction as positive. Okay, so 20, I forgot to mark this one, the distance here is x. Okay, this distance is x, so it's 20 into x and then m1. So m1 is negative 20x. So shear force of bending moment linearly going to vary. And similarly, you can cut the beam from B to C here, and I have marked it that point as 4 for some reason. Okay, so then you write your equation of equilibrium from A to 4, and then you can find out V4 and M4. So I got this value for V4 and M4 this value. So this is the function of bending moment from B to C. This is valid from B to C. I write this one, valid from B to C. And this one is valid from A to B only. A to B. Okay. And next I cut it at 0.6 here. 6. For some reason there's a V5. Cut this one off. Okay. And then this is A, this is 6, and the distance to this point is X. And here also this is 4, this is A, right? And this to this point is X. So once you write the equation, you get this final version. This is valid from C to D. Okay, so we got the functions now for shear force and the bending moment. I'm going to move these functions to the next slide. Okay. Same functions. Okay, and now try to draw my shear force and bending moment diagram. First, look at the shear force from A to B. This is the function. Okay, negative 20. So here to here, negative 20. And from B to C, this is the function. At point B, suddenly it becomes 26. Point B suddenly becomes 26. And up to C, 26. So this is the diagram. So there's a sudden jump like this. And from C to D, this is the function. That means at point C, it becomes negative 14 again. So this is the point. So it jumped down and it remains negative 14 up to point C. So this is the shear force diagram. The hashed area is the area under the curve. Okay. And then look at the bending moment. From A to P, this is the function. When x equal to 0, m1 is 0. M1 is 0. So here. When x is equal to 2.5, you substitute the 2.5. Then you find that it is 20 into 2.5, negative 50. So I mark here, negative 50. So the variation is linear like this. Okay. And from B to C, this is the equation, B to C. So there, when x is equal to 2.5, you can do the calculation and find out the value of that one. That value is equal to, again, negative 50. And when x is equal to 5.5, x is equal to 5.5, you substitute here, and then you find that m is equal to 28. So I calculated that one, m4 is 28. So in between, variation is linear, right? So therefore, this kind of variation. And from C to D, this is the equation. So when x is equal to 2.5 plus 3, 5.5. You substitute the number, you find that again the same point. Okay. And when x is equal to 7.5, when x equal to 7.5, you find that m is this much. When x equal to 7.5 meters, it is 0. So this is the variation. So finally, I get the shear force, so the bending moment diagram like this. This is how you draw bending moment diagram and the shear force diagram using fundamentals. Okay. Any questions? Okay. So hope that you all, I want you all to understand this one, because later in the next 3 lessons, I'm going to directly draw this one using simple methods. But these fundamentals you have to learn first. Okay. Right. So let's try another problem with different kinds of loading. So when the load is changed, you can see that the shear force and the bending moment diagram is different. So here it says draw the shear and bending moment diagrams for a cantilever beam AB of the span L supporting a uniformly distributed load W as shown. So here normally W is given in newtons per meter. Every meter load of W Newton. Okay. From A to B, there's a uniform load, right? But there's no other loads or concentrated loads applied, right? Therefore, from A to B, we expect that the shear force and bending moment going to change continuously. So therefore, we can define the shear force and the bending moment function using one equation. Right. For that, what we are going to do, like before, first draw the freebird diagram if you want. But in this case, you don't need to do a freebird diagram. You will understand it later, because we are going to take a portion which is not attached to the B. So if you want to draw a freebird diagram, you need to draw the reaction forces at B. Right? But I'm going to cut this member from a point C here, C, like this, and then draw a freebird diagram for A to C, and then open up the internal forces and write function for shear force and the bending moment. The cut portion, I have drawn the freebird diagram here, FPD. Okay, now you can see externally applied load is there, and then the internal shear force, a positive one I have marked like this, internal bending moment like this. Okay, so first thing we need to find out, let's say shear force V. So now, as you can remember in the tutorial class, I mentioned that when there's a distributed load, we are going to replace the distributed load with a concentrated load, equivalent concentrated load. So if the distance to C from A is X, right? So this distance is X. The equivalent force, concentrated load here, F, should be equal to W times X, because W is given Newton per meter, right? So the distance is now X into W towards the total force applied. And then forget about W, and we work with the WX, because that is the equivalent force. And it is going to be applied through the centroid of the distribution. Distribution is a rectangular distribution, therefore this is the centroid here. The distance is X by 2. Okay, so you can see here I'm now writing the moment of equation of equilibrium in y direction. So it is negative omega Wx, negative V equals 0, V equals negative Wx. So that means shear force is a linear function. It's not a constant here, right? It's depend on x. When x is equal to 0, V is 0. So here I mark V is 0, x when x is equal to 0. When x is equal to L, my V become negative WL, negative WL at this point. Therefore, shear force variation is linear between those 2 points. So this is my shear force diagram, -1. How about the M? For that, I take my moment around point C and add them all together equal to 0. Okay, first Wx create positive direction moment, therefore positive. Wx is the load, and then multiply by the distance x by 2. And M also in the positive direction, positive M. So finally, I get this kind of equation. It's a second order equation, x squared. There's a parabolic distribution, right? So A to B, shear force variation is parabolic. When x is equal to 0, bending moment is 0. Okay. When x is equal to L, bending moment become negative WL squared over 2. In between, variation is not linear, parabolic. Right? So therefore, I mark that parabolic distribution like this. And the area under the curve shows the third, something else. I will tell you about that one later. All right. So why here the parabolic distribution I mark in that fashion? Why not in this way? This is also parabola, right? But I mark that way. There's a reason for that. You will learn it next week, because the slope of bending moment curve is equal to the shear force at that point. Now here you can see at this point A, the shear force is 0. Right? Shear force is 0. That means bending moment curve slope should be 0. So that means this is the slope 0. That is the reason why it is in this way. But if I draw like this, that means at this point there's a slope, right? The slope is not 0. Okay, so you will understand it next week. Okay, right. So now I have drawn the shear force and the bending moment distribution for simply supported, not simply cantilever beam support applied with uniformly distributed load, and the maximum shear force and the maximum bending moment happens at point B. The values of them are given in here. Okay, so we have done 2 questions on simple bending, all are with transverse loads. And now we know that once we apply transverse load, there's shear force and also internal bending moment. Now, using fundamentals, you should be able to draw shear force diagram and bending moment diagram. So to do that, we need to write the shear force function between discontinuities. Now you know what discontinuity is, right? Load application points are the discontinuities. And then you write the shear force function and the bending moment function for the discontinuities, between the discontinuities, by cutting the member at any point between the discontinuities and drawing our free body diagram. Okay, right. So next, there is a exercise, but I'm not going to do it now. Okay, I will give you some time to digest what we have learned today. It is very simple up to now because we use fundamentals. I want you to go through them again and do some questions in the exercises as well. And there are some videos that I have uploaded to the Moodle course site. Watch them. Okay. With that, I hope that you can build up sufficient knowledge to tackle difficult questions. Now, question number, the exercise given in here is somewhat difficult because the type of loads applied is a bit complicated. I will explain this one next week, but if you want, you can try by yourself, and the solutions are given, and there are some gaps that you need to fill up. Okay. So I'm going to stop here and see you next week. And I will be online for some time. I would like to take up any questions that you have.